Okay, where did we leave off? So last time, where did we leave off? We finished the residue theorem. Residue theorem and applications. The residue theorem says we have a what does it say? We have a function that's meromorphic. So that is holomorphic except for poles, at let's say Z1, Z2, well, finitely many poles in some bounded region R, whose closure is contained in omega. Then if we integrate over the boundary of R is a toy contour, f of z dz, we evaluate this integral, and the integral is 0. No, Anna doesn't buy it. Why not?
It's 2 pi I times the residue.
Right, it's 2 pi I times the residues at the various poles of f. Okay, that was the residue theorem. We saw a bunch of corollaries of that. Yeah, I think we did all the examples. I wanted to. Okay, let's move on to a broader discussion of singularities. Slightly broader discussion. We've seen the power of poles. Here's Riemann's removable singularity theorem. Riemann removable singularity theorem. Very important theorem, as you'll see in a second, has lots of very slick applications. Let's say, well, okay, there's a disk whose boundary is inside omega, but take away some point z0 to f, the holomorphic, and assume that near z0, f stays bounded. Okay, so I'm thinking of, if this is my graph, here's the complex plane, here's whatever, so here's the disk D, and there's some point z0 inside D, and it doesn't have to be a disk, of course, as usual. I'm just making things look simple. You know, we've seen pictures that blow up near this hypothetical singularity. But if it doesn't blow up, if it stays bounded, there's just, you know, I don't know how it stays bounded. Maybe it's going to one point from one side and it's going to another point from another side, right? It could do all kinds of weird stuff that doesn't blow up. There could be all kinds of different types of singularities, right? Smooth functions can do really wild things near a point without blowing up. Holomorphic functions can't. If the function is holomorphic away from that one point z0 and near z0 it stays bounded, then z0 is removable. Bless you. So if you look at the graph of a holomorphic function, it will never do something weird like this. This does not exist. The only thing that exists is it was a nice function, it was a nice curve, and you just forgot a point. Okay? Seems crazy. Seems like it's again, this is complex. You guys are used to me now professing my love for this subject as being too good to be true. And here's yet another instance of that. Okay, so let's look at the integral. So here's our disk D. The boundary of the disk we'll call C. And here's the point Z0. And let's take another point Z inside the disk. So I want to consider the integral 1 over 2 pi I, the integral over this boundary circle. There's no problem with f on the circle. So there's no problem writing f of w minus z dw. Look at that function. Let's call this g of z. Okay. I want to evaluate this integral. But I have two problems with the integrand. So I can't use, I don't know anything about this, this singularity Z0. I don't know if it's an essential singularity, if it's a pole. I can't use a residue theorem. This integrand has singularities at w equals z from the denominator and w equals z0 from the numerator. This is from denominator. This is from the numerator. Right? So instead of integrating over the disk, let's integrate over a toy contour, as usual. So look at the integral, let's call this gamma. Instead, let's look at the integral over gamma of f of w minus z dw. Now, we've avoided the places where f is not holomorphic, where both the numerator and the denominator are not holomorphic, and it's a nice region. And so this integral, we have no trouble evaluating, is equal to 0. Okay, good. Okay, now let the width go to 0. So let's call this eta, and let's call this epsilon, as usual. Let eta, for fixed epsilon, we let eta go to 0. And the top side and the bottom side cancel, and same thing here and here. Just by continuity, we're staying epsilon away from anything where there's a singularity. And so what we find is that the integral over the boundary of a ball of radius epsilon about z is equal to of f of w minus z dw is equal to the integral over this ball of radius epsilon around z0. Does everybody see that? Okay. Sorry. I'm getting a little ahead of myself. Getting a little ahead of myself. This integral over gamma, let's be slightly more careful. Slightly more careful. I didn't say this the right way. The integral over gamma, when eta goes to 0, what do we have? Let's be slightly more careful. We have the integral over the circle. This goes to the integral over the circle, this initial bounding circle, f of w minus z dw. And then these we traverse in the wrong order. If we follow along, we go down and then we do clockwise instead of counterclockwise. Clockwise ball of radius epsilon about z0, and then again clockwise about z. So we get here minus the ball of radius epsilon around z, f of w minus z dw. And again, minus boundary of this ball about z0, f of w over w minus z dw. And that's what's equal to 0. So all I've done so far is let eta go to 0. Let these little windows in the toy contour go to 0. So now I have 3 balls. The ball over gamma, which is actually what I'm trying to evaluate. Then the ball over z, but traversed in the opposite direction, so with a minus sign. And then the ball around z0, also traversed in the wrong direction. Now, this integral, we know exactly how to evaluate because f is holomorphic around here. So what does this integral evaluate to? What does this integral evaluate to? Now we just use Cauchy's formula.
F of z.
Right. So by Cauchy, this is equal to, right, it's f of z. Somewhere I have to divide by 1 over 2 pi I, but I didn't do it, so I have to multiply by 2 pi I. Now let's look at this. So let's look at this in absolute value. Remember, f remains bounded in a neighborhood of z0. The assumption is that f remains bounded near z0. F does not blow up. It does whatever crazy thing it does, but it doesn't, its absolute value does not shoot off to infinity. So I can take away the soup of the absolute value of f near 0, near z0, which is finite. This is just some constant, times what is this integral? Well, what happens to w minus z when I'm in this range? It's not w minus z0, it's w minus z, and w is over here. Yeah, well, it's some fixed distance. So this is also some fixed distance. You know, this is like 1 over z minus z0, let's see, z minus z0 minus epsilon. Something like this. Like, what's the distance from z0, from z to z0? And then the distance might get shorter by epsilon, because w minus z is at least this long. So again, that's just some constant. I mean, this is also bounded above by some constant, certainly as epsilon goes to 0, times the length. Times the length of this bounding curve. And the length of the bounding curve is
Two pi epsilon.
2 pi epsilon. So is everybody following along? So what happens to this as epsilon goes to 0? Yeah, everybody sees. Okay. This is now as epsilon goes to 0. So what do we see? We see that the integral over this circle, f of z over z minus w dw, 1 over 2 pi I, comes out to f of z. The Cauchy integral formula is just as accurate, is just as valid for this function, which has some kind of singularity somewhere else. So what have we just shown? We've shown that this g of z, again, this is what we call g of z. We define this to be g of z. G of z agrees with f of z. But g of z makes perfect sense at z0. Because what are you doing? You're taking f, integrating over the circle. There's no problem with f on the circle. W minus z0. W minus z0 is my universal magic function in the denominator that makes everything possible. So g of z is holomorphic. G of z is holomorphic at z0. And that's the very definition of being a removable singularity. If there's another function that is holomorphic at that point, that agrees with your function. So actually, there was no singularity. We just didn't know that there was no singularity. There was no singularity. That is, it's removable. Okay, does this make sense? So a picture like this does not exist for holomorphic functions. We knew nothing about the singularity except for the fact that it does not, except for the fact that it doesn't blow up in some direction, in any direction, you know, that it remains bounded. So a function that remains bounded in a region, that's it. You don't have any other choice. That function is has a removable singularity. Cool? Okay. Let's use it for some fun stuff.
So
Here's a little
G of
corollary.
Z is holomorphic at Z0 because it's defined in terms of an integral?
Well, it's defined in terms of an integral. F is just bounded on C, and it's W minus Z0.
Okay.
It's defined in terms of, we've changed. You see, the magic thing about this Cauchy integral formula is that you forget what F is. The function is W minus Z.
Okay.
Which is a beautiful function. W is on the circle, Z is inside the circle. They're absolutely bounded from each other. There's no problem with this integral.
Yeah. Okay.
Magic. All right. Corollary. F has a pole at Z0 if and only if F goes to infinity there. It's a very simple observation. Let's prove it. If F has a pole, so let's go this way first. F has a pole implies locally, F of Z looks like 1 over Z minus Z0 to some power times a holomorphic function in the entire region, which is not 0. So locally, in neighborhood, near 0, near Z0. So G is some non-vanishing function. This function, I don't have to argue for you that this blows up, so which implies absolute value of F blows up. That's just from the structure theorem. That's an immediate consequence of the structure theorem. Let's prove the other direction. So assume absolute value of F goes to infinity. Then 1 over absolute value of F goes to 0. Something that goes to 0 means 1 over F remains bounded near Z0. And if you have a singularity and you remain bounded near a singularity, it means 1 over F has a removable singularity at Z0 with what value? Well, we know that its absolute value goes to 0, so its value had better be 0, which is the very definition of being a pole. You're a pole if and only if, by definition, 1 over F has a removable singularity, has a 0, has a removable 0 at Z0. Implies F has a pole. Okay, so pole is a good word for what it is. Right? Pole accurately describes the picture. The picture, if we're looking in the complex plane, you have a pole here. It's because the graph really has a pole. It has to go to infinity. And it's if and only if. Any picture that goes to infinity like that is a picture of a pole. Okay? So remember, just to, it's a non-example, recall, things like e to the z, e to the 1 over z, near z0 equals 0, the graph of that, in some directions it's blowing up, in other directions it's going to 0, and in other directions it's staying, constant size, but moving around, but spinning or whatever. Okay, so this is not going to infinity. This is an essential singularity, and this is not going to infinity. In some directions it is, but in other directions it's not. Okay, so it has no limit. If you go up in all directions, then you're a pole. Cool? Okay. And now we can prove Casorati-Weierstrauss. So theorem Casorati-Weierstrauss. So this is like a baby Picard. You see, look at this function, e to the 1 over z. There is definitely one value that this does not ever take. Zero. This is never equal to 0. Casorati-Weierstrauss is some weaker form of this. So assume f has an essential singularity at z0. Then, for every single epsilon, if you look at f on a ball of radius epsilon about z0, well, take away z0 since it's not defined there. For every single neighborhood of z0, the function is dense in the complex plane. The image is dense. Okay, so if you zoom in on any possible location around epsilon of this point, you will see every single complex number be a limit point. There's a stronger theorem, Picard's theorem, that tells you something more. But this is a very powerful theorem already, and its proof is 1 line, maybe 2 lines. Thomas, something you don't like?
No, I'm just surprised it is 1 line.
As you'll see, well, it's one. There's one idea, and then there's, some yapping to justify the idea. But okay, so let's prove the contrapositive. Proof. Assume there exists a W in C, so that for all Z in this neighborhood, not equal to Z0, f of Z minus W is at least delta. And of course, there exists some delta. So what am I saying here? Here's Z0, here's our singularity, here's a ball of radius epsilon about Z0. And I look at this function, this region, and I see what f maps it to. And I don't know where it maps it to. It maps it to wherever it does. But there's some point W that is not a limit point. That is not a limit point of the image. So for every Z in the range, I stay a distance delta away from W. Okay? Suppose I have this. Let G of Z be the function 1 over f of Z minus W. Okay, so what happens to this near Z0? Near Z0, we just said we never get closer, f of Z never gets closer than delta. So 1 over this is bounded by 1 over delta. It's holomorphic except for, this is holomorphic except for Z0. And near Z0, it's bounded. Gosh, if we only had some way of seeing what happens to holomorphic functions that remain bounded near a singularity. Implies this is a removable. Z0 is removable. singularity. And now there are two possible things. So there is a value for g of z. So we have two options. G of z is equal to 0 or not 0. If it's not equal to 0, what can we say? If it's not equal to 0, then g of z0 is just some value. You know, I don't know what we're going to call it. I could just call it g of z0. It's just some fixed complex number. And that's supposed to be 1 over f of z0 minus w. And it's not 0, so I have no trouble turning this into f of z0 minus w is equal to g of z0. One over g of z0. Thank you. This is non-zero. So it has a reciprocal. So here's the value that you should have plugged f into. In other words, f has a removable singularity. This implies f has removable singularity at z0. Okay? So this function g of z has to take some value. It has a removable singularity at z0. If that value is non-zero, then f itself has a removable singularity. If that value is 0, then 1 over g of z blows up as z goes to z0. G is going to 0. 1 over g has to blow up. 1 over g, of course, 1 over g is f minus this constant w, which means that f blows up, which means that f has a pole. The definition of being an essential singularity is that you're not a pole and you're not removable. What we just proved is that if we miss a point in the image, then f either had a removable singularity or it had a pole, which is the contrapositive to if you have an essential singularity, then in the image is dense. So think about how crazy an essential singularity is. In any neighborhood, any epsilon, get as close to z0 as you want. You're going to see the entire complex plane. There's a big version, there's something called Big Picard. Just as an aside, it has a slightly more difficult proof that we'll skip because it's not one of these one-line proofs. It takes away from my philosophy of complex analysis being, just utterly trivial and everything is follows by one-liners. I mean, the one line, I said it's one line. So what is the one line? The one line is, well, it's right here. Let g of z, the one line is right here. Let g of z be f of z minus w. That's the one line. Everything else is commentary. Okay. So great. Right. I was going to say there's Big Picard, which takes a little bit more work to prove, which says not only is it dense, but actually you hit every single value except at most one, and you hit every value on any neighborhood. On every neighborhood, you hit every value infinitely often. The infinitely often is easy. If you hit it once on every neighborhood, then just take a sequence of smaller and smaller neighborhoods. You hit it once on all of those neighborhoods. That means on the bigger neighborhood, you hit it infinitely often. And you have to allow for skipping one value because this function never hits the value 0. So it's as good a theorem as it could possibly be. It takes a little bit more work, so Google Big Picard if you want to. All right. So that is Casorati-Weierstrauss. Essential singularities are really, really weird. In any neighborhood of an essential singularity, you see the entire complex plane. You're dense in the entire complex plane. Cool? Any questions? So again, it's just easy observation after easy observation chained in this way. All right, let's talk about the extended complex plane. Let's classify meromorphic functions on the extended complex plane. So meromorphic functions on the extended complex plane. What do I mean by the extended complex plane? That I mean complex plane plus, we're going to compactify the complex plane with a single point at infinity. Now you might say, what are you talking about? I can go to infinity in all these different directions. Why am I compactifying it? Why not maybe a circle? Why aren't I compactifying it with a circle of directions or something? Why a single point? So for anyone who hasn't seen this before, do you have a guess? If I said the word stereographic projection, would that mean anything, or does that give it away, or does it give nothing away? Thomas, it gives something away?
Get a sphere.
The sphere, right. So let's talk about the Riemann sphere. Not many people have a sphere named after them, you would think. Spheres have been around for an awful long time. Riemann realized that it's important to study functions on, well, he realized many things. Yeah, let's not talk about manifolds. Let's Let's just look at the Riemann sphere. The Riemann sphere, of course, so I'll call it S or maybe S2. So I want to understand the equality between these two objects, the sphere and the extended complex plane. This is extended complex plane. So here's the complex plane. I'm thinking of this as being R2, comma 0, sitting inside R3, if you like. And then let's put a sphere at the origin at height, with the North Pole at height 1. And we need maps. So we need maps from C to the sphere and backwards, and the sphere to C. Which way would you like to do first?
Sphere to C.
Okay, sphere to C. So I take a point on the sphere. So I take some point. I take some x, y, z, big X, big Y, big Z. Let me call it like that. So this is on the sphere. In other words, I know that x squared plus y squared plus z squared is equal to 1. What am I going to do to get a point on the complex plane? Yes, I'm going to shoot a straight line. Exactly. I'm going to shoot a straight line from the North Pole through this point and get a point. Let's call it little x, little y, or x plus iy. So how do I, gosh, this is going to be a bit of computation. No, it's complex analysis. It's going to be very simple. So I have a point, big X, big Y, big Z. Let's think about the line from this point to the North Pole. What does that line look like? L. So it's parametrized by, let's say, a point T, and it's just a linear combination, T, X, Y, Z, plus 1 minus T times the North Pole. Okay, so this is exactly, and T doesn't have to be between 0 and 1. T can be anything. So I want the value of T so that the Z part of this is 0. So that the Z part, I want to hit the plane at height 0. Value of T such that the Z part is equal to 0. That's what I'm trying to solve. Take 3 seconds and solve it. It really is 3 seconds because all you have to do is look at the value of t at the z parts. Did everybody get this value of t? Okay, so some baby algebra. And therefore, what is the point? So this point, x plus iy, or we can think about it as x comma y, or x comma y comma 0. So this point in the complex plane is equal to, so I just put in the value of t times these things. So this is x times t, y times t, and then I guess I have t z minus or plus 1 minus t, plus 1 minus t. And Thomas is right to be frowning. There was no reason to do any of this. This is z minus 1 over 1 minus z. That's negative 1 plus 1. The whole point of this was that this is 0. So there's our value of x and little x and little y. Pretty simple maps. Okay, let's do the map in the other direction. So that was this map. How about this map? You can invert this, but it's much easier to go from the very beginning and do the geometry again. So now I have a complex point, x plus iy, and I want to find a point x, y, z on the unit sphere that goes through 0, 0, 1. So the line, the new line, is some combination of x, y, 0 and 0, 0, 1. And now instead of wanting the z part to be 0, let's write out what this is. This is tx, ty, and 1 minus t. And we want this to be on the Riemann sphere. In other words, I want t squared x squared plus t squared y squared plus 1 minus t squared to be equal to 1. The sum of the squares of the entries should be 1.
The Riemann sphere we're using, are we using it centered at 0 or sitting on top of the plane?
It's centered at 0, 0, a half.
Okay, so then it's not the collection of points x squared plus y squared plus z squared equals 1.
Oh, I'm sorry. Thank you very
X
much.
squared plus y squared plus z minus 1/2 squared equals 1/2 squared.
Thank you very much. Thank you for catching my about to be typo. Okay, so what do we get? T squared x squared plus t squared y squared. Let's clean this up. What did I do here? That's not a 1/2, that's a square. There we go. So 1 minus t minus a half is a half minus t squared. A half minus t squared is a quarter minus a half times 2 times t plus t squared is equal to a quarter. I'm just squaring. This is a half minus t. And a half minus t squared is that. So the 1/4 cancel. We don't need the quadratic formula for this. We can pull out a factor of t. What's left over is a -1 plus x squared plus y plus t times x squared plus y squared plus 1. Everybody see that? I pull out a factor of t from everywhere. There's a factor of -1, and then everybody else has an extra t in it, and it's x squared, y squared, and 1. So t equals 0. What's t equals 0? That's a fake solution, right? Yeah, that's right, Kailash. T equals 0, just look at it. T equals 0 is the North Pole. Yes, the North Pole is on the sphere. The other solution, of course, so this is the North Pole. North Pole. In other words, t equals 0 is the North Pole. The other option is that this equals 0, and this equals 0 means that t is 1 over x squared plus y squared plus 1. And I mean to be writing little lowercase x's and y's. So if that's how far along this line we need to travel to get to the sphere, not the unit sphere, but the Riemann sphere, then let's go back to what point that is in the line. So the point, big X, big Y, big Z, is given by t times x. So that's little x over x squared plus y squared plus 1. Then same thing for the y squared plus 1. There's a complete symmetry in the x and y. And then in the z direction, there's nothing here. And then there's a 1 minus t here. 1 minus t is x squared plus y squared plus 1 minus 1. Is that right? Is everybody getting the same thing I am? Did I make a mistake somewhere?
I get x squared plus y squared over x squared plus y squared plus 1.
X squared plus y squared
Over
x squared plus y squared plus 1?
I did mental math. I didn't write it down, so I easily.
Well, that's what I'm getting too. That's what I'm getting too. Is that what everybody's getting? Yep. Okay. So I ask you again. So we have these nice maps. We understand sort of geometrically and analytically how to get between the points on the sphere and the complex plane. What's the big idea with the extended complex plane? How come there's one more point at infinity? Anna, you're saying something?
For the North Pole.
The North Pole. The North Pole has no, let's see, the North Pole, if we're at the North Pole, X, Y, Z, how do you connect the line? You see, it's sort of the line, as I approach the North Pole, the point X, Y, however I approach the North Pole, from whichever direction I'm approaching the North Pole, the point X, Y is getting farther and farther away from the origin. And so there's one infinity. There's not a circle of infinities. There's a single point at infinity corresponding to the North Pole. And you can look at this analytically. So North Pole is when Z is equal to 1. So that's, but both X and Y are blowing up. Well, not unless, if Y is 0 or something. I mean, it depends on how you're approaching it, but at least one of these is blowing up as Z goes to 1. So the North Pole is the extra point. And the same thing here. Do we ever reach the North Pole? Does this thing will get closer and closer to 1? This goes to 1, but is never equal to 1. So the extra point is the North Pole. So North Pole in the sphere corresponds to infinity in the extended complex plane. All right, this is a good time to take a break, and then we'll classify meromorphic functions on the complex plane when we come back. Any questions so far? So we had talked about the extended complex plane, and now let's prove a theorem. You have to give you one more definition. What does it mean? So we've talked about holomorphic, meromorphic. What does it mean to be? What is a zero or pole or essential singularity at infinity mean? What does this mean? So definition, it's a pretty simple definition. F has a pole at infinity if the function f of z equals f of 1 over z. Here's the easiest way to access infinity. Bring it on back. Take that infinity and pull it into the origin with 1 over z has a pole at 0. Okay, and similar, same thing with anything else. Pole or removable or essential at infinity if bring the value of z back to 0, where we can speak of things having removable or pole or essential singularities at 0. Okay, does this make sense? So by a pole at infinity, I mean f of 1 over z has a pole at z equals 0. So if you think about this thing having a pole means that near 0, it blows up. The same thing is true for f having a pole at infinity. It means it goes to infinity at infinity. So equivalently, f goes to infinity as z goes to infinity. That's what it means to be a pole. If f grows, however z goes to infinity in every direction, f grows. So I'm thinking of a graph that looks like whatever it's doing here. Maybe it has some other poles, and then it's just going out to infinity in every direction. Then that's what it means to have a pole. Does that make sense?
So if it has a removable singularity at infinity, then there is some value which f approaches as f goes to infinity.
Yeah, and that value is the value of this function at 0.
Okay.
If it has a removable singularity, then this has a value. It might be 0, might not.
Okay.
Yeah. So here's another example. Let's see if I get this right. Yeah. How about just z over z plus 1? Whatever z is, if it's large, then this term is negligible. In other words, I could write this as 1 over 1 plus 1 over z. So this is a perfectly fine holomorphic function at -1. Where's -1? Is this x and this is y? -1 is here. -1. At -1 it has a pole, and then it approaches 1 at infinity. Goes to 1 at infinity in every direction. Okay. All right. So a function has a pole at infinity. Now we know what that means. So here's the theorem. F is meromorphic on the extended complex plane. I want a complete classification. This is a classification theorem. Classification theorem. I want to know what all meromorphic functions on the extended complex plane look like. So if you have some number of poles, some number of zeros, whatever's going on, and then you either go out to infinity or you go to 0, you have a removable singularity at infinity, or you go out to infinity. You don't have an essential singularity at infinity. Then f is rational. is rational. A rational function is a ratio of two polynomials.
So I guess the function cannot be holomorphic on the entire Riemann sphere. Otherwise,
The constant
doesn't-
function.
yeah, it has to be constant.
Yeah. As you'll see, I mean, it follows immediately from what you said will be used in the proof of this statement and follows immediately from this statement. Yeah, in fact, I made a good guess of what such a function will be. Here it is. It's a ratio of two polynomials. Okay. So let's prove this. Proof. The first thing that we have to understand is that it cannot have, if you have a function that is meromorphic at infinity, it can only have finitely many poles. F being meromorphic at infinity means it has finitely many poles. A function that has infinitely many poles cannot be meromorphic at infinity. Cannot just be growing at infinity. I mean, it's sort of clear intuitively. If you have infinitely many poles, you keep doing this up and down dance. And if you keep doing it out to infinity, then you never get to do that uniform growth. Your absolute value is not converging to infinity because there's no distance out that you can go where you stop seeing these spikes. That's the intuition. But of course, there's a very simple reason. So what does it mean to be meromorphic at infinity? This means f of 1 over z is meromorphic at 0. So either it has a removable singularity. So meromorphic means either removable or pole, not essential. Either way, this is, so if it has a pole, if it's removable, then it's already removable. If it has a pole, it's because 1 over f of 1 over z goes to 0. Right? So if pole, then by definition of having a pole, it's that 1 over the function has a pole as z goes to infinity. In other words, 1 over z goes to 0, where 1 over z goes to 0. And so what? Well, what can happen in a neighborhood? In a neighborhood of 1 over z near 0, or let's say in 1 over z in a ball of radius epsilon about 0, can you have infinitely many poles? Yeah, only finitely many poles. Finitely many poles. Otherwise, 1 over f has infinitely many zeros. Else, 1 over f has infinitely many zeros. Okay? What does that mean? You have finitely many poles in a ball of radius epsilon of 1 over z. That means, well, you make epsilon small enough for epsilon small enough, f of 1 over z is regular, is holomorphic, except at 1 over z equals 0. In other words, if we want to make this big function big F of z. So what I really mean we want to say here is big F of z is regular except at z equals 0. Sri, something you don't like?
Regular, what did you mean by regular?
Oh, regular, sorry, regular means holomorphic. Means no pole, no singularities.
Okay.
Regular as opposed to singular. Holomorphic, except at z equals 0. In some ball. Well, then for all z greater than 1 over epsilon, F is holomorphic. If big F is holomorphic has no singularities in a radius epsilon ball, then little f has no singularities bigger than a 1 over epsilon, outside of a 1 over epsilon ball. Okay, so now we have this 1 over epsilon ball. Out here, it's totally holomorphic. Now, F could be if big F of Z has a pole at 0, that is little f of 1 over Z. Then, what does it mean to have a pole? You have some principal part. You have an expansion into a principal part. Let's call this F twiddle infinity of Z plus G twiddle infinity of Z. This is a principal part. And this is holomorphic at 0 and in a neighborhood near 0. Okay, so the principal part, as usual, I mean something like Z to the n plus a n over Z. Okay, inside, I can only have finitely many singularities. So I can have poles for Z less than 1 over epsilon. I have finitely many poles. Finitely many poles at Z1 through ZK, say. And at each one, near ZJ, so in a neighborhood of one of them, here's ZJ, I have an expansion, f of Z is equal to Fj of Z plus Gj of Z, where this is the principal part. So all I'm saying is collect these finitely many principal parts, and there's a principal part at infinity. Let's convert that principal part. You see, we made a principal part at infinity by bringing it to 0. Let f infinity of Z be f twiddle infinity of 1 over Z, and G infinity of Z be G infinity twiddle of 1 over Z. And now look at G of Z, which is f minus f infinity minus the sum of all of the principal parts. So this is f minus all principal parts, of which there are finitely many. So what can we say about G?
It's holomorphic.
G is definitely holomorphic. Yep. Then G is holomorphic. Why? I mean, I've subtracted off these principal parts. The principal parts are holomorphic in neighborhoods outside of, like, if we're worried about neighborhood of Zj, well, f infinity is regular there. It's some polynomial that looks like this. That has nothing to do with that's bounded away from the place where it blows up. This is the part that's blowing up. This part is totally holomorphic. And same thing with all of these. This is the part that's blowing up. This part's totally holomorphic. So I'm taking away the blowy up parts near every pole, including the pole at infinity. So G is holomorphic. In fact, this entire, we've taken away poles in the finitely many places, and we've taken away the pole at infinity, if there was one. The principal part might be 0. But if there was a principal part, we've taken it away.
So it's
So in fact, it
bounded.
remains bounded. Does everybody see that? So Anna, you see the punchline.
Must be constant.
So it's constant. And now we can turn that back around. That implies that f is equal to f infinity plus a sum of these fj's, finitely many of them, plus a constant. But look at what the principal's parts are. There are things that look like this, and things that look like this with a z minus zj instead of just a z here. Those are polynomials. Those are rational functions. You add a bunch of rational functions, you get a rational function. If you have finitely many rational functions, you get a rational function. Okay? So that's it. That's it. The only functions that are meromorphic on the entire complex plane, including at infinity, the only way you get this behavior where you have some poles and then it either blows up or converges to some limit at infinity is if you take a ratio of two polynomials like this. Does that make sense? So, you know, philosophically, what this means, so corollary, is that meromorphic functions on the extended complex plane are determined by are determined up to constant, multiplicative constant, by their zeros and poles with multiplicity. If we know where the zeros and poles are, well, we have a meromorphic function. How do you get zeros? You have we have a meromorphic function, which means we have a rational function. The zeros must be the places where p vanishes, and the poles must be the places where q vanishes. And that's it. So up to multiplying by a non-zero constant, we know everything there is to know about this function. You specify finitely many zeros, you specify finitely many poles. That's it. With multiplicity, of course. So by the, you know, if you like, by the fundamental theorem of algebra, which we proved, or just run this argument again. Okay, any questions? What else did I want to talk about? I guess we can get going on the complex. This is a good setup for the complex logarithm. Things that are determined by zeros and poles. So let's do 8 minutes on the argument principle. Any questions so far? Is all of this making sense? Okay. We're making our way towards a discussion of complex logarithm and the Riemann surface of the logarithm. But let's just think about that for a second. So if I have log of a function, well, what do I really mean by that? If I write f as absolute value of f times e to the I times the argument of f, right? Just polar coordinates. Then what should log do, you would think? It should be log of absolute value of f is a real number. I mean, if log behaves the way logs are supposed to behave, when you take products and exponentiate and so on, this should be plus I times the argument of f. The problem comes in the fact that if I take log of f times g, I want to get log of f plus log of g, right? That's how log needs to have this behavior. And what's the problem?
Well, you might exceed 2 pi, and then you're
Right.
constant off.
Yeah, I've hidden the problem back here. What do I mean by the argument? The argument is only defined up to 2 pi. So implicitly, maybe all of you assume, yeah, it's no problem. Just take this to be in minus pi to pi or something, right? Let's say only one of these sides can be inclusive. The problem is, once I add, I might do exactly what Thomas said and wind around an entire, maybe F winds like this and G winds like that, and the sum of those two things winds around so much that this is off by like some multiple of 2 pi I. Okay, this might be the error in this function. There's another there's a version of this that has no trouble with this error, which is a better function, at least to first order attempt. You see, we'll be off by a constant. What's something that gets rid of constants?
Differentiate.
Differentiate. So if we differentiate, if we just naively, what does it mean? What would d dz of log of a function be if we could define such a thing? If it's going to be anything, it had better be, well, the derivative of log is 1 over, right? 1 over. And the chain rule, f prime over f. So this is a function, this logarithmic derivative, log derivative, is a function that makes complete sense as long as f doesn't vanish. And even if f does, we'll have a pole here. This makes complete sense without any reference to f. So taking the map that takes f to f prime over f is nice. In particular, it recovers this formula that we would like to have for logarithms. So claim, I mean, this is utter triviality, f times g prime over f times g had better be, if we're supposed to be recovering this log-like feeling, we'd better have this be true, and of course this is just the product rule. F prime times g plus f times g prime all over f times g, which in the first term you cancel out a g and get an f prime over f. In the second term you cancel out an f and get a g prime over g. Okay, so there's no issue with this error. And there's a wonderful principle. I think I can do it. I think I have enough time to do it, which is the argument principle. Theorem. This is called the argument principle. Let's do 2 baby versions and then we'll see the general version. If f at z0 is 0 and d contains z0, if you have a 0 and nothing else, and holomorphic and non-zero elsewhere, then the integral over the boundary of d, f prime over f dz, let's compute this integral. Okay, I have some disk d, I have some point z0 where f vanishes. That's why this thing isn't holomorphic. Let's compute, and it has no other zeros and no other poles. What happens when we integrate f prime over f? Okay, let's do this computation. Proof. We'll see what the answer is. Of course, what we're going to do, what are we going to do?
Residue theorem.
Residue theorem, yes, but it's, okay, we have to work out the residue. Well, sure, let's do the residue theorem. Why not? So near z0, what do we know about f? If we have a 0, f of z near z0 looks like z minus z0 to some order times a non-vanishing holomorphic function. Okay. So what about f prime over f? So again, if you take the product of things and you differentiate and you take this logarithmic derivative, it's the sum of the individual logarithmic derivatives. And the logarithmic derivative of g is, well, just g prime over g. And what's the logarithmic derivative of z minus z0 to the n? So I differentiate once, I get n times z minus z0 to the n minus 1 over f itself, z minus z0 to the n. Which means I get to cancel all but one power of z minus z0. So what's the principal part? G, by the way, G is non-zero near z0. So what happens to this? So what's the principal part? This is the principal part. And what's the residue? Residue of f prime over f at z0 is equal to it's the a minus 1. Yes, Hiram, good job holding up an n. It's right here. This is a minus 1. Because it's the term with a 1 over z minus z0 in it. So let me put a 1 over 2 pi I, and I get n, which is order of the 0. Isn't that amazing? You integrate f prime over f, and it tells you what the order of the 0 inside was. Okay, let's do one last calculation since I'm out of time. If f has a pole at z0, then this same integral f prime over f is equal to what? And the proof, let's compute the residue. So near z0, f looks like z minus z0 to the minus n times a function which is holomorphic and non-vanishing in a neighborhood. And by the same argument, so f prime over f is equal to negative n over z minus z0. Again, the negative n comes down and there's one fewer power on top than on bottom, plus g prime over g. And so the residue is negative n, negative order. And so now we can state the full argument principle. So full argument principle, if f is meromorphic on a disk or a toy contour inside a toy contour, then if you take 1 over 2 pi I, the integral over the boundary of that contour, f prime over f. So we're looking at the winding of the argument as like a winding number. I'll explain that in detail later, is the number of zeros with multiplicity minus the number of poles with multiplicity. So every 0 contributes an n, where n is the order of the 0. Every pole contributes a minus n, where n is the order of the pole. So it's the total number of zeros minus the number of poles. It's an amazing, amazing fact. Okay, I have run out of time. I will take your questions